Welcome you all to celebrate communication protocols. So these are all the things which are input devices. There are input devices like keyboard with RS-232 protocol, keyboard with USB protocol, keyboard with PS2 protocol, and mouse with PS2 protocol. These are all the input devices which are communicating with the CPU through ports. And these are all the output devices, our monitor and our printer, which are communicating with the CPU through the parallel port and VGA, video graphics adapter port, as we all know very well. Through the port, one device can communicate with other device. Okay, so if it is a wireless communication, so through antenna, air is a medium. If it is a wired communication, through ports we are going to communicate with one device with other device. This is very, very important. And each protocol have their own ports. USB protocol has their own connector, and RS-232 protocol has the UART protocol or RS-232 protocol has their own connector. Ethernet has their own connector, Ethernet connectivity, and PS2 has its own connector. And VGA port, their video graphics adapter port, has their own set of connectors. And there is a game port and there is a parallel port. So by looking at this, if one board, so CPU is a board which contains motherboard, right? CPU is a system which contains motherboard. Keyboard is a board, and mouse is also having some PCB printed circuit board inside. Monitor is also having printed circuit board inside. Printer is also having printed circuit board inside. So this printer is having some other processor which is a separate product, which is a separate application. Monitor is having some other processor within it. It is a separate product. It has its own processor for processing. Similarly, mouse has its own controller, and keyboard has its own controller. So it is something like one microcontroller talks to another controller, or one microcontroller talks with another processor. So in this context, with respect to this slide, the microcontroller inside the keyboards are communicating with the Core i7 processor, or the microcontrollers inside the mouse are communicating with Core microprocessor inside the CPU, or the processors inside the display is communicating with the CPU. Processor inside the printer is communicating with the CPU. One processor in one board is communicating with another processor in another board. So the exchange of data happening between two boards. This board contains some other processor, this board contains some other processor. So two processors are communicating among themselves through the communication ports. So there are parallel ports, serial ports, and each protocol has their own set of connectors. So from this discussion, what we need to understand is, if we are communicating between two boards, there is a need for standard connector. For RS-232 standard, there is a connector like this. This is called COM port. Normally, we come across the word COM. So this is called COM port, which you call it as D-type connector, 9-pin D-type connector, because it looks like the letter D, where 9 pins in 2 rows. The first row we have 9 pins, 5 pins, and the second row we have 4 pins. So 9 pins in 2 rows is a COM port, which is called as RS-232 port. This was the first communication port, which was introduced long back. Now laptops are coming with HDMI protocol, and some of the projectors are with VGA port. So now we normally use VGA to HDMI protocol converter, that small cable. So parallel and serial, there are two ways we can communicate with one device with another device, as we see. So through parallel port, we can communicate with the printer, long back, and through serial ports. Other than this, all the USB is also a serial port, and RS-232 is also a serial port. VGA is also a serial port. Ethernet is also a serial port. PS2 is also a serial port. So serial port has its own significance because it occupies very less space. Because you see, parallel port means it is occupying more space, parallel port connector. But if it is a serial port, means it is occupying only very less space when compared to this. And now you have, this is the USB common connector, right? But now you have micro mini connectors, and the advancements of technology is reducing the size. So serial communications are mostly preferred. Parallel communications are very rarely preferred, where we demand very high speed data transfer. There only we use parallel communication. In rest of the places, we use only serial communication. So our VGA is also serial communication. RS-232 is also serial communication. USB is also serial communication. Keyboard is also serial communication. So everything is serial communication, as we all know. So parallel and serial communication. So when we talk about parallel communication with respect to 8-bit. So nowadays we have 32-bit and 64-bit data processors which communicates parallelly. But now here we do 8-bit parallel communication as we look at the screen. So here data to be transmitted. So when it is 8-bit, it is very easy for us to understand. So if it is 8-bit data to be transmitted and received. So for example, data to be transmitted and received is, say for example, 1001 and 0110, which is binary. In decimal, if you want to call, means it is 150. In hexadecimal, if you want to say, we can say it is 96. So 96 is the hexadecimal value which need to be transmitted parallelly. So let us say this is a transmitter. Let us say this is the receiver. Transmitter contains D0 to D7. There are 8 pins. D7 is MSB and D0 is LSB. So 1001 and 0110 are the 8 bits which need to be transmitted parallelly. And there is a receiver D0 to D7 which also should receive parallelly. And we need to connect D0 pin to D0 pin of transmitter to D0 pin of receiver. D1 pin of transmitter to D1 pin of receiver. D2 pin of transmitter to D2 pin of receiver, D3 pin of transmitter to D3 pin of receiver, similarly up to D7 to D7. So it is connected like this. So 8 pins, that means 8 pin of transmitter is connected to 8 pin of receiver, something like this. So 96 is being transmitted and 96 is being received parallelly as we see here. So this is parallel communication as we all know very well. One thing we need to understand, in 1 second, 8 bits will get transmitted because it is parallel. If it is serial, in 1 second, one bit will get transmitted. So in 8 seconds only, 8 bit will get transmitted. So 8 times the speed is reduced if it is 8-bit serial communication. Similarly, if it is 16-bit serial communication, 16 times the speed is reduced. At least we do 32-bit communication. So 32 times the speed is getting reduced if it is 32-bit serial communication. But if we use 32-bit parallel communication, 32 times the speed is increased. That you need to understand. So right now we are looking at 8-bit parallel communication. If it is 32-bit parallel communication means when compared to serial 32-bit serial communication, 32-bit parallel communication will improve the speed 32 times. Among all several peripherals, RAM is the only peripheral which can interact with the microprocessor up to some maximum speed. So the RAM is a peripheral which communicates with the processor up to a maximum speed. So the only place where the parallel data transfer taking place today is between the random access memory and the processor in the motherboard. Okay, so which uses a communication protocol called PCI. So peripheral component interconnect. We used to call it as PCI, peripheral component interconnect. Nowadays we use PCI Express. There is something like PCI Express. PCI Express is a parallel communication protocol. So through this protocol, we can communicate with the random access memory and the processor in the motherboard. Okay, so other than PCI Express, that means other than data communication between the processor and the random access memory, all other communication happening in the world is serial communication. That you need to understand. Only one parallel communication with respect to our knowledge is our random access memory inside the microprocessor communicates with the microprocessor parallelly. Other than the communication between the processor and the random access memory through PCI Express, all other communication is happening only serially, which is very, 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 very important. So simply what communication we use means simply by closing your eyes, all of us can say only serial communication is happening. Something like that we can say. It is very, 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 very important. Because very rarely we use parallel communication because wherever we demand very, very high speed, there only we need parallel communication. Okay. So PCI Express is a parallel communication protocol that you need to understand. Okay, so 8-bit parallel communication is this. This is how it works. So I'll show you one slide which will be very interesting. So understanding parallel communication. So parallel data transfer takes place within the processor between registers and the CPU for high-speed communication. So data transfer between the processor and the RAM is parallel for high-speed data transfer. So let us look at this picture in the slide. So this is the processor, right? So this is the processor. The square box is the processor, and this is the RAM slot in the motherboard. So this RAM in the motherboard is communicating with the processor only parallelly. So these are all the connectors. So normally 64-bit connectors because all the processors are 64-bit processors today. So there are 64 wires which will go from this random access memory to the processor. So the RAM communicates with the processor parallelly. That is the moral that is very, very important. You need to understand. Okay. So the diagram shows the gigabyte motherboard, which shows the random access memory and the processor are connected in parallel. All other data transfer is only serial to meet the low cost, less space, and low power requirements. Okay. So low cost means what? If it is a 64-bit parallel data transfer, if we are transmitting for 1 meter means we need to purchase 64-meter cable. 1 meter for 1 bit, 2 meter for 2 bit, 64 meter for 64 bit. So if the parallel data transfer need to take place for 1 meter means we need to purchase a 64-meter cable. The cost is 64 times than the serial port. Hence, it is better to go for serial port if we go for a parallel data. It is better to go for low cost. If you go for parallel port in a 64-bit communication means the cost is 64 times of the serial communication as we discussed, right? Plus space, 64 wire goes from one place to another place means it is something like a mat. You can go and sleep on the mat. Up to that level, it is that much wider and that much space it will occupy, which is very, very important. It is something like we are putting a floor mat or something like this. 64 wires are going like that means this occupying much space, which is the second thing. But if it is a serial communication means only one wire. It's fantastic, right? Then low power. So logic 1 means 5 volts. We used to say logic 1 means 5 volt with respect to TTL logic. Logic 0 means 0 volts with respect to TTL logic. In digital electronics, we have studied, right? If it is 64-bit parallel communication means we need 64 5 volts. First case, if all the 64 bits are 1 means we need 64 5 volts. Then only we can say 64 bits are transmitted. So 64 5 voltage source is required kind of thing. So the parallel power communication consumes very large amount of power. So for low cost, for less space and low power requirements, always we demand serial communication. Hence, except data communication between the random access memory and the processor, all other serial communications, that is all other communications are only serial communications. That is the message, that is the understanding from this particular slide. How the serial communication takes place, that we need to understand in a simple way. So understanding the serial communication here. Okay. So there is a transmitter and there is a receiver. So earlier we have seen the parallel communication like that. Now we are looking at the serial communication, 8-bit serial communication, where the transmitter has D0 to D7. There is only one wire here, which is TXD. There is one wire here, which is TXD. There is one wire here, which is TXD. And there is another wire here, which is RXD. There is one wire here, which is TXD. And there is another wire here, which is RXD. So only one wire is connecting. Earlier we have connected 8 wires. Now we have connected only one wire. So instead of 8 wires, we have connected only one wire because it is serial communication. TXD means transmit data. RXD means receive data. The same 69. Now let us say that data to be transmitted is 69. Okay. So data to be transmitted is 96. I have given it as 96. And D0. So MSB. Okay. Let us assume the data is transmitted is 69. So D0110 and 1001. So 69 is the data which need to be transmitted. So now you see how the serial communication takes place. Forget about the data. Now you see how the serial communication is taking place. So internally data transfer is happening parallelly. You see internally data communication is happening parallelly. You see parallelly data comes up. You see parallelly data comes up. And serially data shifts out. Serially data shifts out. That is why all the serial communication transmitters, all the transmitters are parallel in serial out shift register as you see in the screen. All the transmitters are parallel in serial out shift register as you see. Data are entering parallelly and then serially it is going to shift out. So all transmitters are parallel in serial out shift registers. All receivers are serial in parallel out shift registers, which is very interesting. Okay, you see parallelly data is entering and then serially data is about to shift out. But in the receiver side, data will enter serially and then parallelly it has to send out. So serially in parallel shift register is in the receiver side, parallel in serial shift register in the transmitter side. Whatever might be the protocol do you have today, we are very much comfortable with Wi-Fi, we are very much comfortable with Bluetooth wireless communication, They are very much comfortable with USB. All are serial communication as we discussed right now. Whatever may be the protocol, whether it is a USB or Wi-Fi or Bluetooth or Ethernet or whatever might be the protocol, its transmitter is going to be parallel in serial out shift register, and its receiver is going to be serial in parallel out shift register, because the communication happens within the processor or controller is parallel, but the communication happening between the processors are serial. So if one processor need to communicate with another processor, means there is a need for parallel in serial out shift register in the transmitter side, and there is a need for serial in parallel out shift register in the receiver side, as we see in the screen. So this is a very simple and very elementary model. Similarly, in 8-bit, similarly in 16-bit, we have a 16-bit parallel in serial out shift register. If it is a 32-bit processor, we have 32-bit parallel in serial out shift register. If it is a 64-bit processor, we have a 64-bit parallel in serial out shift register. So that is the one we need to understand. So for convenience, for comfortness, we are doing with 8-bit. That's it. Now let us see how the parallel in serial out shift register is shifting out the data. You see, first bit is shifted out, then second bit is shifted out, third bit is shifted out, fourth bit is shifted out. When the corresponding bit is shifted out, means it is entering the receiver. So one bit is shifting out, means from the transmitter, means the same bit is shifting in the receiver. So the sixth bit was transmitted, the sixth bit was received by the receiver, seventh bit was transmitted, and seventh bits were received by the receiver, eighth bit was transmitted, and eighth bit was received by the receiver. Now the transmitter is empty. So parallelly data was entered the transmitter and it is shifted out serially. And serially data was shifted in. If all the 8 bits are received, then the data is going inside the processor parallelly. It's very interesting. So you can see parallelly data is coming in. You can see parallelly data is coming in, and serially it is getting shifted out. So parallel in serial out shift register in the transmitter side, and serial in is happening now. After all the 8 bits are received, this data is communicated internally parallelly like this. That is why this animation is showing very clearly. Internally data is communicating parallelly, but it is receiving serially, hence serial in parallel out shift register. So from this animation, you could have experienced up to some extent, you can celebrate. So parallel in serial out shift register is in the transmitter side and serial in parallel out shift register in the receiver side. Any protocol, whatever may be the protocol, today what we are using right now, whether it is a wired or wireless communication protocol, all the transmitters are parallel in serial out shift registers. All the receivers are serial in parallel out shift registers, no doubt about it. That is why we have studied shift registers in our digital electronics, and the applications of shift registers is in serial communication. Fantastic, right? That is how you have to relate digital electronics with microprocessor. That's why every day, or whenever time comes, we are saying that programmable digital electronics is microprocessor. This is another justification to say the programmable digital electronics is microprocessor. So in digital electronics, we have studied parallel in serial out shift registers, serial in parallel out shift registers. One of its application is serial ports. Today we are talking about USB. In USB, you have transmitter and receiver. Definitely, the transmitter is parallel in serial out shift register, receiver is serial in parallel out shift register. Whether it is an Ethernet, yes, transmitter is parallel in serial out shift register, receiver is serial in parallel. Is it Wi-Fi or Bluetooth? Whatever it is, all the transmitters are parallel in serial out shift registers. All the receivers are serial in parallel out shift register, as we see right now here. So it's very interesting. There is something like peer-to-peer communication. So point-to-point communication is peer-to-peer communication. If there are only two people, A and B, so A talks with B or B talks with A, this is called as peer-to-peer communication. If more than two people are communicating, means it is called as networking. That we know very well. Then based on the direction of data flow, communication is broadly classified into simplex, half duplex, and full duplex, as we know very well. Simplex, data transmitted from A to B. That's all. Only one direction. A good example is radio and TV receivers. So radio receivers and TV receivers. Normally we utter the word television receiver. Why? Because television can only receive, television cannot transmit. So very good example for a simplex serial communication is television receiver. Used to call the radio as radio receiver because it can receive alone. Radio cannot transmit. Our FM radio cannot transmit. So television receivers, radio receivers, they are only receivers. Hence it is simplex. What is the transmitter? The broadcasting station is transmitter. So PSG FM is a transmitter. FM station is a transmitter, something like that. This is simplex. Then we know half duplex. So A to B or vice versa. But at a time, A can communicate with A is transmitter or B is receiver, or then B is transmitter, A is receiver, as like the ball game that we have seen in the previous class, but not at a time. So very good example. We used to say walkie-talkie. All the police officers are used. Traffic police officers are people are using this. All of us know very well. So now fuel duplex. Simultaneously, both the transmission and reception can take place. This can happen only when we have two communicating wires. This can happen only when we have two communicating wires. So very good example is universal asynchronous receiver transmitter. When we say UART means you can call it as universal asynchronous receiver transmitter. So where you have two wires, just now we have seen TXD and RXD. So TXD is a transmit data, separate wire for transmission. RFD is a receive data, which is separate wire for receiver. If there is two wires in the same IC, one for transmission, another for reception means, so through TXD you can transmit and through RXD you can receive. So simultaneously we can both transmit and receive. Hence, UART is a very good example for full duplex serial communication. So Ethernet is also a very good example for full duplex serial communication, because Ethernet is also having TX plus and TX minus and RX plus and RX minus. Hence, it has a separate wires for transmission and reception, Ethernet. Hence, Ethernet is also a good example for full duplex communication. All the wireless communications are half duplex, whether it is Wi-Fi or Bluetooth or whatever it is, because if there is only one antenna, the answer antenna either it can transmit or antenna either it can receive. Yeah, transmission and reception cannot happen simultaneously. So people are talking about MIMO, right? Multi-input, multiple output. MIMO, only in MIMO type of antennas we can expect full duplex serial communications in the wireless communication. Based on the direction of the data flow, serial communications are broadly classified into simplex, half duplex, and full duplex, and these are a few examples. Now we are very much interested in communication between two devices. We are not concentrating much on the networking. So what are the mandatory requirements for communication? Interest between, as yesterday in the last class we have discussed, interest between both the transmitter and receiver is mandatory for communication. So it is something like handshaking. Hello, how are you? I'm so and so, something like that. If I meet Raj Kumar first time, normally I'm very much familiar with Raj Kumar, but I have never seen Raj Kumar. After the pandemic, when we meet Raj Kumar in the classroom, I will say, hello Raj Kumar, very nice to meet you in person. Virtually we have connected, now only we are connecting in person, something like that. We will handshake with myself and Raj Kumar, both of us will do handshaking. And that is the first step in communication. After handshaking, we'll sit together and then we will discuss, and then we can exchange the valid informations, etc. So if Raj Kumar is not interested to talk with me, when I approach Raj Kumar will not show his hand, he will run away. Raj Kumar is not showing his hand, he is running, means there is no need for any further communication. Something like that it goes on. If the handshaking is proper, then we can say the further interaction may happen. Okay, so that is what with respect to human beings. But with respect to computers, it is something different. So for a communication to take place, synchronization between transmitter and receiver is necessary, as we discussed yesterday in detail. How synchronization can take place? Synchronization can take place in two ways. One is baud rate based synchronization and clock based synchronization, that we will discuss detail soon. But with respect to baud rate based synchronization and clock based synchronization, first in the game, first what we should do is, I should say that I am ready. First of all, I am available. Transmitter is available, something like that I should say. So there are two things. There are several things which you have to concentrate. First, I should say I am available, number one. Then receiver also should say I am also available. That's the first thing. In terms of devices, if you see, the transmitter is switched on. The receiver is switched on. That is very important. The first and foremost requirement for communication is the presence of both the transmitter and receiver in terms of human beings. But in terms of system, presence of system alone is not important. The system must be switched on. Okay, something like that. Okay, so it must be switched on and saying that, okay, I am alive. So somehow the transmitter should inform that I am alive, I am switched on to the receiver. and the receiver should say, I am also switched on, I am also alive, something like that. This is the first information which need to be exchanged between both the transmitter and receiver. So the transmitter says I am alive to the receiver through one signal. That signal is called as data set ready, DSR. Data set ready, DSR. You can very well remember my name. My name is D. Sivaraj, DSR, D. Sivaraj. So the transmitter is ready, D. Sivaraj. That is data set ready, something like that. So the transmitter is ready, DSR. So DSR is the signal which goes from transmitter to the receiver in RS-232 protocol. So after receiving the data set ready signal, the receiver will acknowledge the transmitter that I am also ready through data terminal ready, DTR, data terminal ready, which is very interesting. So this is the first bidirectional data transfer saying that transmitter is also ready, that is transmitter is ready and receiver is also ready. So transmitter is present, DSR signal says that transmitter is present, alive. DTR from the receiver to the transmitter says that yes, receiver is also alive. So both the transmitter and receiver are switched on and they are ready for communication, something like that. So let us say the transmitter is PC and the receiver is printer. Printer might be printing. So printer is ready, available, but the printer might be printing. It will take some time to read the data from the PC. So PC should get the acknowledgement from the printer before it sends the data to the printer. Okay. So next synchronization signal is request to send. Request to send. RTS is request to send. So the PC will request the printer, can I send the data, something like that. So after completing the printing job, the printer will say, okay, now my receive buffer is clear. You can send the data through clear to send signal, CTS signal, clear to send signal. So after receiving clear to send signal, now the transmitter will send out the data. Send out the data means parallel serial shift register data transfer will take place as we discussed right now. DSR is the signal going from transmitter to receiver saying that transmitter is ready. DTR is the acknowledgement from the receiver saying that data terminal ready. Then transmitter is requesting the receiver, shall I send the data, something like that. Then the receiver is acknowledging the transmitter by clear to send, something like that. So after this, for synchronization, now both the transmitter and the receiver are comfortable to exchange the data. Now the transmitter will transmit the data through TXT pin and the receiver will receive the data through RXT pin. So these are all the first four are the synchronizing signals and the last two are the communication signals, which is with respect to the RS-232 serial communication protocol, which was the first protocol which was invented long back. So this is the RS-232 connector, which you have seen in very old PCs. So this is the D-type connector, 9-pin D-type connector, where 5 pins are in the first row and 4 pins are in the second row, which is called as COM port, which is a serial port. So whatever we have discussed is available in this pins. Let us say you can see this first pin, you can see data carrier detect. There is something like data carrier detect. And what about the second pin? Receive data, RXD. What about the third pin? Transmit data, TXD. What about the fourth pin? Data terminal ready. What about the fifth pin? Fifth pin is ground. What is the sixth pin? Sixth pin talk about data set ready. And seventh pin is request to send. And eighth pin is clear to send. And the ninth pin is ring indicator, something like this. So except this data carrier detect and ring indicator, we have discussed other signals. So this is how through RS-232 communication, data was exchanged long back, 25 years back. This was the first communication protocol, which is COM port, COM1. So today we use USB and a lot more communication protocols. They are all virtual COM ports. So they may be COM port 5, COM port 3, COM port 4, COM port 20, COM port 23, 43, etc. But COM1 means it is only RS-232 port, something like this, which is 9-pin D-type connector, and the signals are like this. So there you can observe that data set ready is here, data terminal ready is here, request to send is clear, clear to send is here, and receive data and transmit data. All these signals, whatever we have discussed so far, is being available here. This is very interesting and very important to understand and very important to celebrate. So such a connector is there in this CPU as we see, and the keyboard which was there during 2000. This is the keyboard during 2000 when we are doing our undergraduate, when we are doing our 10th standard, 12th standard. We used to work with the keyboard, computer keyboard like this, and this keyboard has a RS-232 connector. Communication happens between these two boards only through this COM port, which is COM1 port. This is the universal synchronous CPU transmitter frame. You can call it as frame. Why? Because you can say the first bit is D0 bit. D0, D1, D2, D3, D4, D5, D6, D7. This is 8 bit, which is one character. So 8 bit means 8 bit data. This is an 8 bit data. There is a start bit and stop bit. There is a stop bit and stop bit. There is a parity bit for checking the errors. In the communication, if there is an error means there is a parity bit. So there is a start bit and there is a stop bit and there is an error detection bit called parity bit, and there is a message bits which is an 8-bit message D0 to D7 as we see here. So the numbers also very important. LSB first, MSB next. The first start bit, first bit is LSB, least significant bit, followed by, and the 7th bit is most significant bit. Then there will be a stop bit. Now you can ask, while doing serial communication, what is the need for start bit and what is the need for stop bit? So which is very interesting, we need to discuss. Start bit is the bit which is something like knocking the door, because always we should close the door, otherwise unwanted entry will happen. So to prevent the unwanted entry into the processor, always it is mandatory to close the door. So what start bit will do? Start bit will knock the door of the RxD pin. That means through RxD pin, start bit will knock the door. Hello, there is the serial data. Please open the door. Something like that, which is start bit. What about stop bit? Stop bit will close the door. Stop bit will close the door. Start bit will open the door for serial communication in the receiver. Stop bit will close the door for the serial communication in the receiver. This is very interesting and very important thing. Okay, so who will send the start bit? Transmitter will send the start bit. Who will send the stop bit? Transmitter will send the stop bit. So the receiver will understand data is about to start from the start bit. The receiver will understand data communication is over through stop bit. So how a microcontroller identifies something is happening in the pin, which is very, very important. How a microcontroller identifies something is happening in the pin, which is very important. The microcontroller identifies something is happening in the pin only through transition in the pin. If there is no transition in the pin, none of the software algorithms or any artificial intelligence algorithms, any deep learning algorithms or any machine learning algorithms will fail to detect what is happening in the pin, which is very, very important. So all the algorithms will work inside the processor, which can execute the code, but in the hardware, in the pin, we must know what is happening in the pin means only through transition in the pin we can identify. So transition in the pin means there is only two possibilities of transition in the pin. The one possibility is transition from 1 to 0. Another possibility is transition from 0 to 1. So if there is a transition from 1 to 0, that is called as start bit. As you look at the screen here, it's very interesting. So there is a transition from 1 to 0. If there is a transition from 1 to 0, then you can call it as a start bit. If there is a transition from 0 to 1, then you can call it as a stop bit, which is very, 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 very important. It is independent. It is independent of any protocol: Wi-Fi protocol, Ethernet protocol, CAN protocol, flux array protocol, Bluetooth protocol, SPI protocol, I2C protocol, any protocol that you study, for whatever might be the protocol, there is a need for stop bit and stop bit. Without start bit and stop bit, there is no possibilities of communication. And please remember, all the start bits are transition from 1 to 0. All stop bits are transition from 0 to 1 as you look at the screen. So from this, what do you understand? If there is a transition from 1 to 0 in the RxD pin, the receiver will understand the transmitter is willing to communicate serially with us, something like that. And if there is a transition from 0 to 1, then the receiver will understand the one communication part is over. So there are so many things beyond this, but right now you need to understand why start bit and stop bit in any serial data transfer or in any serial communication, which is very, very important. UART stands for Universal Asynchronous Receiver Transmitter. Similarly, USB. Similarly, Ethernet. Similarly, CAN frame. But whatever may be the frame, definitely there will be a start bit and there will be a stop bit. And start bits are only transition from 1 to 0. Stop bits are only transition from 0 to 1. What is start bit? Why it is needed? Start bit knocks the door if the receiver is knock the door of the receiver to open the door. Start bit from the transmitter open the door of the receiver. A start bit notifies the receiver to get ready to receive the serial data. What is stop bit? Why it is needed? Stop bit closes the door of the receiver to prevent the junk data entering the receiver. Or stop bit notify the receiver to stop receiving the serial data. How does the receiver understand someone is willing to transmit? Through stop bit. How does the receiver understand transmitter is willing to stop communication? Through stop bit. So the summary of what we have discussed is very well given. So with respect to 8051 microcontroller, we have full duplex universal asynchronous receiver transmitter. Because it has two pins, TXD pin and RXD pin, it comes under full duplex. Okay, so there is a full duplex universal asynchronous receiver transmitter available in our inside our 8051 microcontroller. And if you look at the block diagram, the bottom right corner block of the block diagram is serial port, where we can observe that there is a TXD and RXD. And one more thing you need to concentrate here. So if you see the pin TXD and RXD pin, then you can say it is UART communication. If you see the pin SDA and SCL, you can say it is I2C protocol. If you see the pin something like D plus and D minus, then you can say it is USB protocol. And if you see the pin like MO, SI, MI, SO, slave, select, and clock, then you can say it is an SPE protocol. If you see something like CAN high and CAN low or recessive or dominant, then you can say it is a CAN protocol. So by looking at the pin label, we can identify which protocol it can support. So wherever you see TXD and RXD pins in any microcontroller, then you can proudly say that this microcontroller supports Universal Asynchronous Receiver Transmitter UART, which is very interesting. With respect to 8051, we have only one UART. Because it is Universal Asynchronous Receiver Transmitter, it has a TXD pin and it has an RXD pin, as we see in the screen. In the data sheet, if we see the internal block diagram of the UART serial communication, here I am justifying that SBUF. SBUF is a serial buffer. SBUF is a serial buffer, which is the parallel in serial out shift register. As you see, this is the TXD pin. So this is very interesting to celebrate. This is the TXD pin, which is going out, which is P3.0. In a pin diagram, if you see, this is P3.0. Sorry, P3.1 is TXD, P3.0 is RXD. So P3.1 is TXD and P3.0 is RXD. So this is the P3.1. So internally, from the internal bus, data enters the SBUF. SBUF is a serial buffer. So the paralleling serial out shift register of 8051 microcontroller is called as SBUF. In some other microcontroller, it will be called as some other name. You may call it as transmit buffer or whatever it is. But all the transmitters are parallel in serial out shift register. The parallel in serial out shift register transmitter in 8051 microcontroller is called as SBUF. So SBUF is a serial buffer which is parallel in serial out shift register, as you see the screen, as you see in the cursor. So this is the shift register and this is the transmission control. The shift signal, control signal is coming here, and through the AND gate data will be shifted out, and through this OR gate data will be transmitted through TXD data. So this is available in the serial communication data sheet. We can look at it and to celebrate much better. And there is a control register called serial control register, SCON register, SCON, serial control register. So the serial control register contains 8 bits, and there is 4 modes, as like 4 modes of timer operations. Timer 0 is a 13-bit timer, timer 1 is a 16-bit timer, timer can operate in 8-bit auto reload mode, timer can operate in split mode. As there are 4 modes, if we can operate the timer in 4 different modes. Similarly, serial communication can also, we can use 4 different modes. As we see in the bottom table, there are 3 bits for mode selection, SM0, SM1 and SM2, among which SM0 and SM1 are shown here in the bottom row. When SM0 and SM1 are 00, it can operate in mode 0, so shift register mode. And if the SM0 and SM1 are 01, then it is in mode 1, which is 8-bit universal asynchronous receiver transmitter mode, and the baud rate means variable baud rate. I'll talk about baud rate, right? I'll talk about baud rate soon. And if it is 10 means it can operate in mode 2, which is 9-bit UART. If it is 11 means it can operate in mode 3. which is 9-bit UART. So SM0, SM1 are the most significant 2 bits, which is going to select in which mode we are going to operate the serial port. And SM2 is for multiprocessor communication. So right now we are going for only communication between 2 processors. Whenever we are interested in networking, we are in need to use the SM2 bit. So SM0 and SM1 are the 2 mode pins. And REN means receive enable. You can see enables the serial reception, set by the software to enable reception, clear by software to disable reception. So if you don't want to receive anything for a period of time, we can make this bit as 0. And whenever we are ready to receive, then we can make this bit as 1 in the SCON register. If we want to say do not disturb means we can make this bit as 0. So even though some other processor is willing to communicate with us, they cannot able to communicate with us. Why? Because we have closed our ears, something like that. We have closed our ears. We are not interested to receive anything. I think most of you are made this REN bit as 0. Among 60 plus people here with us, I do not know how many of you have made this REN bit as 1. If your REN receive enable bit is 1 means then only whatever I am transmitting which can reach you. If your REN bit is 0 means the signal what I am transmitting will not reach you. TB8 and RB8 is the 8th bit. There is 9th bit which is needed for multiprocessor communication. And very important thing, there is something like TA and RA, so which we need to discuss here, which is very interesting. TA and RA. Transmit interrupt flag and receive interrupt flag. So this you have to see here. There is something like transmit interrupt flag. So in the serial communication, what we have discussed here, which is very important. You see, parallel communication is happening just like that here, like this, just like the. But in the serial communication, the bits are shifting out one by one. Now the first bit is shifted out. Now the second bit is shifted out. Now the third bit is shifted out. Now the fourth bit is shifted out. Now the fifth bit is getting shifted out. So it is 8 times lower than the parallel communication, right? It is 8 times lower than the parallel communication. Because it is 8 times lower than the parallel communication, before all the 8 bits are shifted out, please try to understand, before all the 8 bits are shifted out, we should not put this data in SBUF unnoticingly. We should not put the data in the SBUF unnoticingly. Say for example, at this time, if you are putting, if you are reloading the SBUF means the 5 bits of the first byte and the first 3 bits of the second bytes will get transmitted, and the receiver will receive the first 5 bits of the first byte and the LSB 3 bits of the second byte, and it will consider that as a 1 byte. So this is a big disaster in serial communication. So to ensure all the 8 bits are shifted out and the transmitter is empty, then only we have to put the data once again in the transmitter side. So to notify the programmer that all the 8 bits are shifted out and the transmitter is empty, 8051 microcontroller has transmit interrupt flag, which is very important. 8051 microcontroller has transmit interrupt flag to notify all the 8 bits are shifted out. This is very important for any serial port because the shifting out happens very slowly. Without knowing all the bits are shifted out, if we reload the parallel serial shift register with the next byte, so total confusion will happen. I hope you understand what I am trying to say. So to ensure that all the 8 bits are shifted out, some flag should set. With respect to 8051, there is a TA flag. So TA flag notifies all the 8 bits are shifted out from the transmitter. Now the transmitter is empty. Now you can put the data in the transmitter, next byte in the transmitter, something like that. The same thing will happen in the receiver side. So when before 8 bit have reached, if now say for example only 4 bit has reached the receiver, unnoticingly we can copy the data from the serial in parallel shift register, means this byte 4 bit and the previous byte LSB 4 bits we will receive unnoticingly. So we should wait until all the 8 bits are shifted in. So how to wait until all the 8 bits are shifted in? When all the 8 bits are shifted in, somehow it has to notify. How it can notify? With respect to 8051, it is notifying through RI flag. So where are those flags? Those flags are in the SCON control register. You see, fantastic, right? This is how you have to celebrate. You see, RI flag, you can see now you can understand what is TI flag. Transmit interrupt flag set by the hardware at the end of the 8th bit time in mode 0 or at the beginning of the stop bit of the other modes in any serial transmission must be cleared by software. Receive interrupt flag is RI flag set by the hardware at the end of the 8th bit time. That means at the end 8th bit is received means RI flag will set. When RI flag set, that justifies receiver is full. So when we are programming for a receiver, we have to wait until RI flag sets. When we are programming for a receiver in a serial port with respect to 8051, we have to wait until RI flag sets. When we are programming for a transmitter with respect to 8051, then we have to wait until TA flag sets. When TA flag sets, that justifies all the 8 bits are shifted out and the transmitter is empty. When RI flag sets in the receiver side, all the 8 bits are shifted in, receiver is full of data. Now it is time for us to take the data from the S buff. So RI flag notifies the receive buffer is full. TI flag notifies the processor that transmitter is empty. Fantastic, right? Transmit interrupt flag notifies the processor that transmitter is empty in the serial port. RI flag in the receiver notifies the processor that the receiver is filled with some data. Processor, you come and take the data and make use of it, something like that. So TI and RI are the notification for transmitter empty and receive buffer full in both the transmitters and receivers with respect to 8051 microcontroller, which is available in SCON register, serial control register. So we have to set the mode, and then while communicating, we have to look at this TI flag and RI flag because it is bit addressable. This bit TI bit can be checked independently and RI bits can be checked independently. While transmitting, we have to check TI flag, and while receiving, we have to check for RI flag. Okay. So for time being, I am stopping with this.